So let me start. So we are going to talk about a little bit about set theory because it's a language. Well, it's useful to know set theory because it's often the probability statements are stated in terms of the set theory. So, okay, so this is a set theory. And in addition, I'll talk a little bit about indicators of sets, which is not in the book, but it's so useful that kind of I want to tell it. Maybe it's somewhere in the book, but not at this chapter. So in second indicator functions. So we kind of have usually we have a kind of something like probability space. It's the number of the all possible outcomes, so possible elements, and we have subsets of this overall global set. So, and the basic relation in the set theory is that omega belongs to A. And so there is an outcome, so it's element of a set and it belongs to A. Maybe kind of I give here an example. So we can have omega equal to say 1, 2, 3, 4, 5, 6, and say A, it's something like maybe all 2, 4, 6, all even numbers. And so we can say about, say, 2 that 2 belongs to A, and say about 3 that 3, doesn't belong to A. And so this is a basic notation. And after that, we define things such like intersections of the sets. And so we can say that A intersect B. And then what it means. So by definition, well, it's also set. So it's set of outcomes such that, and maybe kind of, I'm not sure, maybe column. So with such as that omega belongs to A and omega belongs to B. Right. And then so here, for example, we could choose some kind of B equal to say 1, 2, 3. Then so the A intersect B will be all elements that both are in A and B. So we would have something like, so what is, so kind of what is the both on them? So we would find that we have 2 in both of them, right? So it would be a set which consists of one element equal to 2. So this is intersection. So here is a small thing is an implicit that, so we know what is AND. And so, and then we know what is AND, but implicit, well, kind of, if you're mathematician, we can ask, what do you mean by AND? Right, and well, after that, it's going a little bit, well, formal, but in principle, we can say what it means that 2 belongs to A. And well, so it's just a relationship which says that if you, it's like a kind of functions which says that 2 belongs to A, it means that there is a function on A which kind of to each, there is a function of all on all omega, which to all element of this omega put in correspondence false or true. So here, for example, for A is equal to 2, 4, 6, right? We would have this corresponding. We would say, so how we would characterize A? A would be, it would be kind of a correspondence which would say A false, 2 true, 3 false, 4 true, 5 false, and 6 True. Now it's a little bit more clear what we mean by this relationship. It's just a function. So we all know it's a function, kind of just kind of a map. And so just a function on all elements of a global set, which maps 1, 2, 3, 4, 5, and 6 to false or true, right? Right. So kind of, so well, and so this is characterization of a set. If we kind of want to program something, so and we want to program a set, then we would have a list of all elements. And if we want to say this is a set A, we would kind of program something like that. It would be a vector, kind of a vector such that to first element it would be false, to second element it would, this vector would have a true, third component of this vector would be false, fourth component would be true, and so on, right? So this would be kind of a representation of a set in which computer is which is easy to understand to computer, right? So now, right, so this is a representation of this thing, right? And well, so let me kind of immediately say so kind of what's the indicator function of this set. Okay, so maybe and after that I'll tell how it relates to this intersection, which so the indicator function of a set is just kind of instead of false you write 0, instead of true you write 1. And so because kind of well false or true, so computer also kind of doesn't know what is false or true. He knows 0 and 1. And so indicator function of a set A is a map is a function okay, so function, so I'm not sure if I kind of write it clear, function. And so now by definition it would be something like f of omega, so function on omega, which is defined like this. F of omega is equal to 1 if this omega belongs to A, and 0 if omega doesn't belong to A. And so this is an indicator function. So if in this particular example, so we have this set A. And so, and kind of we have here false, but kind of it's the same thing. It's a false. It means that it's not on the set. It means we can put here 0. Here we put 1. Here we put 0. Here we put 1, 0, 1. And so this is indicator function of A. And so it's a simple. It's a vector, and kind of and the component of this vector, which corresponds to element omega, is equal to 0, 1, depending on whether this omega is in the set or not in the set. And so this is why kind of it's useful, because well, if you program, well, if you want to try to explain to the kind of a computer what it means a set, what it means of these operations, you better have something like that kind of easy to understand to computer, and zeros and ones, vectors is something which is very easy to understand, which is very easily understood by a computer. Right. And so now, right, so what it means. So now I say so this is omega belongs to A and omega belongs to B. So now how we can write it in terms of indicator functions. So right, for this we need to understand what is AND means, right? AND means kind of, well, AND means AND, of course, it's clear, but in principle, in terms of, so kind of, this is a mathematics, and the part of the mathematics logic, kind of formal logic. And in this part of the mathematics, in formal logic, we have a AND, right? It's an operation which works like this. So you have a true false table. And so if it's true and true, it's true. And in every other case, it's false. So, and so if you look at this and say, okay, so what about if I put instead of true, I put 1 and 0 here? Can it kind of, does it mean something in normal kind of operations, not in the end? And it just means multiplication. So if you have if you put here zeros and ones, and so this is a and how it worked if the true was represented by 1 and false represented by 0. It's actually it's truly how it's represented in the computer. Well, maybe with some modification, but true is represented by 1 and false is represented by 0. So if you look at this, you see that this is just a multiplication. So here's 0. And so you just multiply these things and you'll get this thing. So now that means that we can write here, we can write actually how to calculate indicator function of A intersect B in terms of the indicator functions of A and B. So it would be 1A intersect B is equal to, okay, so this function f at omega, I wrote f of omega, apology. So it's usually denoted 1 or I, and with subscript, so to understand what we are talking about, we set or I and omega here. And so this is the indicator, the definition of indicator function. And so now if we have an indicator function for A and B, so here's indicator function for A, so maybe I'll write indicator function for B, kind of don't have a space, but kind of maybe I still kind of remove here. And so let us see how we can calculate things. So for B, 1B, right? It would be 1, 2, 3. So it would be 1, 1, 1, 0, 0, 0. Right? So the first 3 elements, it's truths. 1 belongs to B, 2 belongs to B, 3 belongs to B. All others are zeros. So if we want to calculate what's the function, indicator function for intersection, we just multiply these 2 vectors component-wise. So this would be kind of the rule. So A of I and B is equal to 1 of A multiplied by 1 of B. And so this is a function. So it depends on the omega. Right? So in principle, we can write here omega. Omega. It's function. It's component-wise multiplication. And so now again, so this is not so important, but it's very useful kind of. It turns out that this is very useful in if you want to kind of represent sets in computer science and you do calculation in the probability theory, in many cases, it's very useful notation. And so this is intersections. So, right. So now let us check that this is kind of agrees. So 1 to 0 is 0. So all products here will be zeros, except 1. 1 times 1 will be equal to 1. Okay, so we will get a function. So I don't have a place to write it, but we will get a function. Maybe kind of I remove all this stuff, and I don't have much things to remove. So it's not enough space here. Right? Okay, so we have a function which have just 1, 1, opposite 2, and all other elements are zeros. Okay. So questions about this? So this is kind of this whole long speech about intersection of two sets. And, but it's kind of makes easy to talk about other things. So this is intersection. Second operation is union. Right. And then union of two sets, it's the omega, all outcome such that, so this is such that omega belongs to A or omega belongs to B. Okay, so now let us do these examples here. Okay, so now here was A intersect B. Here is A union B. Okay, so we take a union, so it's all elements. 1, 2, 3, 4. So 5 is absent. So kind of 2 was in both and we counted. Okay, so it's omega belongs to A or omega belongs to B or to both. So that's why kind of 2 is okay. 2 was in both, but we mean by or, we mean not exclusive or, but irregular or. Okay, so now 1, 2, 3, 4. 5 is absent. 6 is here. So 6. Right? So this is a union. So now, well, kind of we can try to do the same thing. So we know how to write down indicator function for the intersection, just component multiplication of the vectors. So we can write down the indicator function for the union. Right? So we can write indicator function for A union B of omega is equal to what? Right? Okay, so now for this, well, it would be nice if it would be addition, but addition doesn't work because kind of addition would move 2 ones to 2 and 2 doesn't have any meaning. Okay, so we write what is OR means. Okay, so let us write immediately in terms of ones and zeros. So 1 means true, 0 means false. Okay, so if 1 and 1 true is it's 1 true, and so this is true and this is false, then we have true, here's 0. Okay, so the only time when two statements or of two statements is false is when both of them are false. Sorry, yeah. So if I'm saying today is raining and today is pretty warm weather, so today is raining is false. Today is pretty warm weather, true. So the result will be true. Right? I need to say 2 false statements to get the false of or of false. I need to say something. Today is raining and today is very cold. Okay, so now we have this table. Right? And so we want an operation such that some arithmetic operation such that would be true. Right? So, well, we can use new notation, right? So there is a new notation, kind of, you just kind of can write it. But, well, if you want to do calculations, maybe kind of it's, do calculation, don't remember anything, kind of just kind of do calculation with functions, with irregular arithmetic. And you need to write something like, right? So, and what is this? Right? It's something like a opposite of this thing. So you can write that this is something if you sum things and subtract the product. Right? Right? So for example, here's if you sum 2 ones, you'll get 2, and you subtract the product, you get 1. Here, if you sum 1 and 0, you get 1, and you subtract the product, you will get 1. Right? And so here's you add this together, you get 0, and you subtract the product, you get 0. So it's actually sum minus product. So you can write here, this is equal 1 of A of omega plus 1 of B of omega minus product of 1 of A, 1 of B of omega. And so okay, so this is kind of, this is this thing. And so this is just a regular plus minus, no or, no kind of anything. So this is very nice, kind of calculationally you can kind of, so this is a product component-wise product. This is component-wise sum, but this is just a regular operation on vectors. All right, so now what else? So we know how to do intersection. This is the union, and the last operation which is relevant is so maybe not sure, kind of, let me kind of remove something maybe here. Let me remove this thing and write 3 here. So, and this is complement. And so now complement. So this was intersection, section of sets. This was union of sets. And this is a complement of a set. And then now, so we have one set, say A, and we want to complement. And so there is 2 notations. So I kind of usually, I accustomed to write AC. And so this is important. This is kind of confusing because I sometimes write AC, and I think in the books it's A bar, and I think that both are more or less standard. So, or A bar. And so I like this one more because it's kind of, well, in topology, this would make something like maybe, well, I don't know. This is also kind of, so this is just kind of 2 possible notations. I think that the book uses this one. And so what is it? So by definition, C is the set of omega such that omega doesn't belong to A. So in this particular case, it would be, so what it would be? It's A is 2, 4, 6, so the complements all are all numbers which are not in this set. So a complement is equal to 1, 3, 5. And so now kind of, so okay, so what's the indicator function for the complement? So here's a more simple term. And or, it's and you need 2 statements. Here you need just 1 statement. So not is you have a true, you have a false. And so how it works so it moves 1 to 0 and 0 to 1. Right? So this is not, it's kind of, I can see what, when you can write in is 1 minus 1 over A of omega. And so this is a, and so probably the only thing that I have not wrote here is inclusion of the 2 sets. It's a kind of very trivial. And so A is included in B if omega belongs to A, implies that omega belongs to B. So if we know that omega is in A, so well, kind of in probabilistic terms, it means that A happened, that it would mean that B also happened. Okay, so it implies. So if this is true, then this is also must be true. Right? Okay, so now, if this is false, right, so this is false, then it might be that this is still true. Right? So kind of, if something is false, then it doesn't say anything about. So kind of, if you have a 0 and 1s, then implies means that this 0 can be. So this is a. All right. So kind of this is one. So but it's kind of it's more or less clear. So kind of the only kind of thing that to keep in mind that if omega is false, then it can be anything here. Right? And so now let's look at, for example, at this particular example. So we have 2, 4, 6, and B is equal to 1, 2, 3. Right? So we have one element here, 1, which is in B. Right? So it's true, but it's not in A. So we know that B is not in A. Right? So another way also kind of A is not in B, but it's kind of intuitive thing. Right. And A is not in B. And so now, from the point of view of indicators, you can also formulate it means that so this thing. So this is an example, and so this is maybe written here. So it's in this particular example. So A is not. In this particular example, A is not in B. And in this particular example, B is not in A. In this example. So this is a more general statement. So more generally, kind of, we would say, so when suppose we know A, indicator function of A, indicator function of B. And so how we can check, kind of, so let ask the computer to check if A and B, kind of, so you know it how to do it intuitively, right? So kind of, but how to check the computer? Well, computer should check whether one of A is smaller or equal than one of B. He should check that it's true for every omega. And if this is true, then this is implication false. And because if it's 1, this should be 1. If it's 0, if it's at some element it's equal to 0, false. Then it can be 1 or 0, doesn't matter. Right, so this is a formal thing. So now, okay, so questions about this. Okay. Now, two things. Okay, so this is a formal thing, but informally it's useful. Well, kind of, it's not very useful, but if kind of you want to kind of to see it graphically, when you draw Venn diagrams. Okay, so. Actually, Venn diagrams are not so helpful. It's just helpful to kind of understand what's going on, but not helpful in calculating. So one exception is, well, kind of simple exclusion problems. In this case, it's very useful. But here, so if you have A and you have a B, so these are kind of circles which represents two sets. You can think about as a geometric sets, kind of points. And so this is an intersection. A and B. right? And this is the union. So A and B. And so if you want to figure out so this is the union. If you want to figure out what's the complement, you need to kind of to draw the whole space. So this is the whole space. And so here is A, and everything outside of A would be a complement. So this is graphically, this is thing. So this agrees with this very formal approach. Very formal approach is better because you can calculate things. Right? So even if we kind of, when you stay graphically and kind of there is a formula which includes a huge number of intersections and complements, and so graphics is not so good, but kind of you can feed this formula into a computer, at least it can calculate things for you. All right, so now I promised the Morgan laws, and so before the Morgan laws, you have a distributive laws. Also, let me kind of get how I wrote them. All right, so A, B, and C. Okay, so there are two distributive laws. So A, intersect first. Okay, so this is intersection, this is a union, and you can write it that this is A intersect B, union A intersect C. And so this is, you think about that this is a multiplication and this is addition. So this would be regular distributive law. So A multiplied by B plus C would be equal A multiplied by B plus A multiplied by C. And so and second law is A union B intersect to C is equal to A union B and union. So okay, union, so intersect A union C. So this is more difficult to write down. There is nothing like that in the regular arithmetic. So think about this as a multiplication. That would become something like A plus B multiplied C is equal A plus B multiplied by A plus C, which is not true in the regular arithmetic. And so here these two operations satisfy two distributive laws. And so now this is distributive law, and you have also De Morgan laws. De Morgan laws. So this connects union and intersection, and De Morgan laws connects unions and complements, and so it adds complements actually. So again, so how I wrote it here. So A intersect B, and I take a complement of this. Right? So it turns out that this is A complement, and here instead of intersect, I put union, B complement. So complement of the intersection is equal to the union of the complements. Right? So this is easy to remember. Right? So if you take if you take some operation and complement on the result of this operation, the result will be complements of the sets, and you change the operation, and there is another symmetric law. Say here we would have a B union C, sorry, A union B complement is equal to A complement intersection B complement. Yeah, so this is so distributive law not so well, not so very often used, not so very often. This is used very often, kind of De Morgan's laws in calculation. So now it's actually not, it's just it's a kind of theorems. You can prove it. So how you can prove it? So you can prove by in two ways. One way is to check things. So for example, I want to prove 2. Then I have 8 cases. Okay? So we can have, so one case, for example, let me try anything. So omega belongs to A, omega doesn't belong to B, and omega doesn't belong to C. Right? So for example, so I choose any arbitrary. So there are 8 possible combinations, right? So kind of it could be omega belongs to A, omega belongs to B, omega belongs to C. So kind of can be omega doesn't belong to A, omega doesn't belong to B, omega doesn't belong to C. So 8 possibilities. And so this is one of these possibilities, and I look, say, on second law here. I just verify that second distributive law is true, what it says. And so it says that, so what is this thing? So let me calculate. So second law verification. And so it says, I need to calculate, so let us calculate the left-hand side and the right-hand side. So the left-hand side, B intersect to C. So for this particular case that I consider, omega doesn't belong to B and omega doesn't belong to C. So this thing is false. Okay? So you should look for me because I can make a mistake. So this is false, intersection is false. Okay? So after that, A is true. Okay? So true and false, and you take the union. So or, this is or operation. Okay? So it means that true and false, should be true. Okay? So the left-hand side, so what we checked actually, we checked that omega belongs to A union B intersect to C. Okay? So just for this specific case. And so now we are looking at the right-hand side and calculating, say A union C. A belongs to A, so this is true. A belongs to kind of omega belongs to A here, so this is also true. Right? True, and here is operation AND. So intersection of two sets, it corresponds to operation AND, so this is also true. So we know that omega belongs to A union B and intersection A union C. And so now it means that for this omega, this is okay, kind of omega belongs to both of them. And so if we would find that omega belongs to this thing but doesn't belong to it, this would be bad. It would mean that these are different sets. And so now after that you sit and check for kind of 8 cases. And so this is one possibility to do it. And so now, and every of these laws can be proved in this way. Right? So here just kind of you need, in this particular case, maybe 4 cases because there are only 2 sets here. And so for these 2 cases, 8 cases. So now, so one benefit of the indicator function can be checked here because now you can prove this by using indicator function. It's a long calculation, but it's straightforward, and you don't need to do any kind of case-by-case checking. So let me kind of do it. It's not very long. It's just tedious a little bit, but it's not very long. So let me kind of write it. And so let us write the indicator function for this thing. And so we write A union B intersect C. And then I will not write omega because it's understood. Kind of this is a function. So it's equal to 1 of A. So, and we're writing for union. So remember, it's sum minus product. And so 1 of A plus 1 of B intersect C minus 1 of A multiplied by intersect B and C. It's by definition of this thing. Not by definition, but the kind of definition of the property of the indicator function for the union. Right? So this is clear, right? So just write union as a kind of operation of indicator function of A and B intersects C. Sum of this thing minus product of these two things. Right? So now I want to write everything in terms of A, B, and C. So I need to write this as an indicator function of B and C. This is just a product. Right? So I write that this is equal to 1A plus 1B multiplied by 1C minus, here the same thing, this is a product. So we have here 1A, 1B, 1C. Right? So that's it, kind of. I cannot do anything more than that. And so this is kind of the result. So this is the indicator function of this guy written kind of in, and this is a regular operation, multiplication and so on. Component-wise, this is kind of functions. So you can think about the vectors. And so now what about the other side, this one? So 1A union B multiplied by 1. So sorry, maybe kind of here, let me write it first. A union C. So this is this thing, right? So it's equal. Okay, so this is intersection, so it's a product. 1A union B multiplied by 1A union C. Right? Okay, so now after that, I want to write down these things. A union B, A union C. Okay, so it's equal to 1A plus 1 B minus 1AB one A, one B. So this is the definition for this thing, and multiplied by 1 over A plus 1 over plus 1C minus 1A multiplied by 1C. Now I use the regular distributive law. I kind of remove these brackets and kind of write it down. What is it? So now let me check if I'm going right. So now I'm starting to suppose that I maybe made a mistake because I don't remember that I calculated this way. No, yeah, it's okay. Yeah. Seems to be so far. Okay, so now multiplication. Right, so 1A, right, and 1A, 1C plus 1A, minus 1A multiplied by 1A multiplied by 1C. And so this is multiply 1A by this thing and use the distributive law. And after that, I write 1B multiplied by 1A plus 1B multiplied by 1C minus 1A multiplied sorry, 1b multiplied by 1a multiplied by 1c. And the last one is this thing. So plus 1a, 1b multiplied by 1a plus 1a, 1b multiplied by 1c and minus 1a, 1b multiplied by 1a by 1c. Right? So I kind of like I probably should write it simpler, but I kind of just here so far kind of it's okay, right? So right. I just kind of open the brackets. Right? And after that I say, well, okay, 1a times 1a. Right? So what is this? So kind of, right? So 1a is something like a vector 1, 0, 0, 1 or something like that. And if you multiply it by itself, I take the square of it. Right? So I'll get the same vector. Right? So if I multiply it by itself component-wise, when 1 multiplied by 1 will be 1, 0 multiplied by 0 will be 0, 0. So kind of, if you take the square of this vector, it will be the same vector. So I can use the property. I can use the property that 1a times 1a is equal to 1a, and 1b multiplied to 1b is equal to 1b, and 1c multiplied by 1c equal to 1c. So this is kind of simplifies. So kind of, so what we'll get if we simplify this thing? So we will get 1a here, 1a, 1c, nothing, no simplification. Here's 1a times 1a times 1c. So minus 1a, 1c. Here, 1b times 1a, no simplification here. Plus 1b, 1a. Here's 1b times 1c, no simplification, plus 1b times 1c. Here's 1b, 1a, 1c, again, no simplification. So minus 1b, 1a, 1c. So plus 1a, so 1a, 1b, 1a. So 1a times 1a, 1a, so plus 1a, 1b. Here's 1a, 1b, 1c. Plus 1a, 1b, 1c. And the last one, 1a, 1b, 1a, 1c. So 1a times 1a is 1a. So it's 1a, 1b, 1c minus 1a, 1b, 1c. And so now we cancel out everything which we cancel. This is the same thing, so we cancel out. Now what's other things? So we cancel out 1b, 1a and c, no cancellation, so I may probably made a mistake somewhere. So this cancel out, maybe no. This is, I don't like this thing because they sum to 2. And they should cancel out, so probably I made a mistake somewhere here.
I believe you dropped a negative sign from 1A, 1B.
Yeah, I believe so, but in which of them?
The last one. Yeah, that one.
This one. 1A, 1B. So what it's come from? Let me look at what I wrote, and kind of hopefully I wrote kind of so here's so minus here, minus here, minus here. Right. Now over here I made it. So you are saying let me look again. So this is This is minus here, right? This is 1B, 1A, 1B, 1C. Yeah, but this seems to be fine, so it's plus, right? So here.
I think it was supposed to be minus in the first place too. Right there.
So it should be minus, you're saying it should be minus here, right? So
Yeah, I think so.
So, right, so this has come from 1A, this has come from, yeah, so because this is, sorry, yeah, this is multiplication of this thing times this thing, right? So this has a minus sign, so it has a, okay, so it should be minus sign, right? So, but then this should also have a minus sign, right? And this should have a plus sign, right? Because this is, so I forgot about minus here, so all signs here should change. And so now what it means here? Well, it's okay. So here should minus, here should be plus, sorry. So it should be also minus, and here should be plus. This doesn't influence this thing. So it's cancel out, but yeah, thank you. And so, okay, so this is 1 over n over b. This is cancel out, and we'll get, okay, so the remaining terms are this one, 1a plus 1b, 1c, minus 1b. So, well, we can, this is multiplication, so it's commutative. We can write a 1a, 1b, 1c. We can change places kind of here, it's commutative. And so we compare this thing and find this is exactly the same thing. And so we proved it. So this is slightly faster because I was not have enough energy to write down 8 cases to check this law on the 8 cases. And here, well, it's pretty tedious and I made a mistake, right? But it's it's straightforward. You just write function, expand, and then they check it, this is the same thing. And so this is one of the kind of illustration. What's the benefit? The benefit is that of using indicator functions that you don't need to check many cases, right? It's just one calculation. Okay. So now we know what is the De Morgan laws. And this is basically everything that I wanted to say about the set theory. Okay, so any questions? Okay, so now we move to the discrete probability models. So let me remove all this stuff. So essentially, this is only serve as a language and maybe in some calculation. It's not very will not be very useful in the following, except that when we define conditional probabilities, we will need to know what is the intersection. And an intersection is basically end of two statements. So if one event and we claim that both events happen together, then it corresponds to the intersection symbol. All right, so discrete probability models. So what is the discrete probability model? Discrete so even not model, probability spaces. So omega is a discrete probability space. right? If it is finite or countably infinite. So finite is clear, right? So finite means that it has some specific number of elements, and countably infinite means that it have a infinite number of outcomes, but we can count them. So omega equal to 0, 1, 2, 3, 4, and so on is okay, right? But omega equal to interval 0, 1 and all points in that is not okay. So not okay. And this is just a theorem by Cantor, so which was kind of very surprising at some when it was discovered that you cannot count the this set, so you cannot put it in bijective correspondence to this set. So this is basically what it says. And so why kind of we know we need the so we need this space definitely because there are something like results, some experiments which result in the uncountably many outcomes. Something like a shooting on the target was one example. And so why we need this thing? Well, we also have an experiment which have a countably infinite outcomes. For example, if you throw a coin, right? So and look at when the first head occurs. Right? So you don't know when it happens. Right? So it might be on the first throw of the coin, on the second throw of the coin, the third one, and in general it can be on any. So you'll need a countably infinite probability space. And there is a big difference between these discrete probability spaces and continuous probability spaces, just because we can write down sums over countable elements. Right? So we can say, let's sum the probabilities of all outcomes. And this is a valid thing. So you can, in the finite case, it's just a finite sum. In the countably infinite case, it's not as finite sums, but you can write it as a series. And in calculus, you learn that you can sum the series. And so you can find what's the limit of the series if it's convergent. And so it's also a well-defined concept of a sum here, sum of the probabilities. So here you cannot say, let us sum over all possible cases, over all possible probabilities if every kind of element here has non-zero probability, so kind of, right? So because there is no good definition of what its sum means in this case. You cannot, there is no good definition of a limit in this case. Limit of a sum. So there is a good definition, but it becomes integral and density, and this is what we study later. So this was an attempt. So when people defined the integral, it was an attempt to extend the sum to the countably infinite spaces. Sorry, uncountably infinite spaces. Right. All right, so now, all right, so in this situation, so now we are looking at discrete probability spaces. In this situation, it's very easy kind of models. So for discrete probability spaces, probability of event A for any event A, right? So an event, remember, it's subset of outcomes of the experiment which you are interested in. And so just kind of, you can write it. So this is a probability of A. So it's equal to the sum of P of omega. Where omega is overall outcomes which are in A. Right. And so why is this true? I know, so this is kind of, I'm saying this, but why is this true? It's just like axiom. If you think about, you have an axiom of a Kolmogorov which says so that if you have if you kind of decompose the set A into mutually exclusive pieces and want to calculate the probability of this A, then you need to calculate the probability of each piece and sum them together. Okay, so here's, you just say you take every outcome inside it. So you take omega 1, omega 2, omega 3, omega 4, maybe infinite number of them, right? But countable. And after that, so by axiom, you know that by the third axiom, you know that if you want to calculate the probability of A, it's the sum of the probability of each element, because it covers this, the union of these elements covers all the set A and they're disjoint. So this is equality, is just kind of restatement. Well, yeah, kind of a restatement of axiom. And if you think about experiment, it's also kind of clear. So you want to calculate what's the probability that some outcomes occurred. So what's the frequency that some set of outcomes occurred in an experiment, right? So if you do this experiment many times, so you look at the frequency of one particular interesting outcome, on the frequency on the other particularly interesting outcome which comprise this event. Third outcome, right? And after that, sum these frequencies together. If any one of them is realized, then event A is realized, right? So this is also can be interpreted in terms of the frequencies of A in the experiment, but from our point of view, it's just consequence of the axiom A. So everything was already kind of is in axioms. Everything, the relationship to experiments is already kind of in axioms. And so now let me give a definition, which is again not with the book but it's natural definition. So kind of definition, and it's maybe not kind of so standard, but I think it makes kind of sense. So P of omega equal to the probability of the set omega. Okay, so this is omega is elementary outcome is called the probability mass function. And so you think about this as kind of that's well, so this is mass function is just kind of borrowing from the physics. You can think as about as a mass of one particular outcome, of every particular outcome. And if you want to find out what's the probability of the whole set, so these outcomes, you think about them as a points, kind of, then you kind of sum their masses. And so now, so again, so this is a little bit not standard, because usually what people talking about is a probability mass function of a random variable, and we will talk about it later. But it's kind of nice thing to keep in mind is that kind of with discrete probability spaces, you can think about kind of, if you want an analogy, physical analogy, when you think about, so this is outcomes like a points in some space, and every outcome has some mass associated with them, So kind of, if you want to figure out what's the probability of particular set, right, particular event, you just sum together all the probabilities here, probabilities of each point in this set. Right, so when we are talking about discrete variables, it will be something like that, and it's kind of, it will be just kind of specialization of these things. All right. Now, so here's maybe an example here. Again, very simple example. So, so this is just an illustration, so not real example, not very difficult kind of, but so unfair die. So, and so, so we have here probability. So it's again, so the space omega is equal to 1, 2, 3, 4, 5, 6, and probability of 1, probability of 2, probability of 3 is equal to, sorry, probability of 3, sorry, 5. So odd outcomes is equal to 1/4, which is not standard, should be 1/6 for the fair die. And probability of 2, probability of 4, probability of 6. Well, you can figure out what is it if it's equality. So sum of all probabilities should be equal to 1. So you can figure out, so if you calculate it, turns out it should be equal to 1/12. And so sum of all probabilities by axiom should sum to 1. So sum of all probabilities should be equal to 1. And so when you say, so what's the probability of the event, say 1, 3, 5, or maybe 1, 3, 6. And so you say that this is 1, 3, 1/4 plus 1/4 plus 1/12. And it should be equal to something. And so this is what I'm saying. So just kind of to calculate things that we need just to sum this probability, and this is unfair. So this is the difference from Laplace definition. So this is a generalization of Laplace definition because we are thinking about this P omega. In Laplace case, we would be all equal to the same thing. Here, we're all equal to the different things. They might be equal to the different things. Right? All right, so this is a discrete probability phase. A recipe how to calculate probability in this way. So there are a couple of laws which are useful. Right? And I think that these laws actually not only for the discrete probability case, but they are easier to see here. And so here's a law. So maybe kind of where I should write it. Some probability laws. And when we say laws, it's just a consequence of the axioms. Kind of you can derive them from the axioms. So, and I probably will not derive most of them, maybe one of them. So one of them is what if you have a probability of the, what if you want to calculate the probability of a complement? Well, it's equal to 1 minus the probability of A. So, because A and its complement together, they give the whole space and they're disjoint. So they don't have, they're mutually exclusive or disjoint, it's the same thing. And so, so they don't have anything in common. So if you use the axiom 3, which says something about additivity of the probability of the mutually exclusive sets, and you see that probability of the AC plus probability of A should equal to the probability of the whole space, which is 1. Okay, so this is how you calculate the. So this is the first very simple law. Second law is monotonicity. It's all kind of, well, so probability of A, so sorry. If A is subset of B, so B is larger, it contains some other outcomes, then probability of A is smaller than equal than probability of B. Okay, so because if you kind of add the probabilities of, let me kind of ask you. Excuse me, can you be a little bit lower because I'm teaching right now. All right, so because if you add some additional elements, then the sum of the all outcomes, the sum of the probabilities can only increase. Right? So this is also a evident thing. So here's the third law. This is a more interesting, so probability of a union. Right? So if you write the probability of A union B, so now you would want to write something like probability of A plus probability of B. But it's kind of, it would be right if they were disjoint, if they would be mutually exclusive, and it would be right by the axiom. Right? But I never said that they're exclusive. So some outcomes can belong to both of them. Right? So it turns out that in this case, you'll need to subtract. You need to subtract probability of the intersection of them. Right? So now, why is this true? So this is maybe kind of something that you want to prove. Let's say, so if you want to prove it, then we kind of just have this formula how to calculate these guys. Right? So you can write that probability of A plus probability of B is equal to, and so here we write the sum, the first one, omega, which belongs to A, probability of these outcomes, plus, this is kind of by our formula, the probability of A, plus sum of omega belonging to B, probability of omega. Okay, so now, and after that we write, all right, so this is equal to sum of omega belonging to the union A union B. Right. So here may be kind of a good thing to draw a picture. Okay, so this is A, this is B. So some outcome is omega. So omega 1, omega 2, so omega 3, omega 4, and so on. Right? So some outcomes are here. So the first sum is the all outcomes in A. Right? The second sum is over all outcomes in B. Right? So they cover all A and B. So that's why I can write that it's sum of all omega in A union B, P of omega. But if I write here, kind of, right? So if I write here, when I see, well, okay, so here I count omega 1, omega 2, omega 3, omega 4 in this sum. In this sum, omega 3 was counted twice because it belongs both to A and B. So P of omega 3 was in both of these sums. Right? So I counted it twice. And here I counted it just once. Right? So you'll need to write down that this is equal to add this undercounted elements. So you can write that this is P of omega, right? And which elements you counted twice here. The elements which were both in A and in B. So it's omega belong in A intersect B. Right? And after that you see, all right, so what it means, what this formula gives you. It gives you that this is equal to the probability of A union B plus probability of A intersect B. Okay, so if you look at this, so probability of A plus probability of B equal to probability of union plus probability of intersection, and compare this formula, you see that this is the same thing. Okay, so this is the same formula. And so this is a proof of this third law. Right? And in principle, kind of this is a this is a law, but this is a theorem, and you can extend it. So what you can say, what's about if I want to calculate the union of three sets, the probability of the union of the three sets. So there is a formula, and you can get it by the similar thing that by looking at kind of sums like that, and after that figuring out which you undercounted and now overcounted. So you can write this thing. So you can write that P of A union B union C. So the first thing will be P of A plus P of B plus P of C. But this would be too much, kind of. So here you subtracted the probability of intersection, right? So you subtract the probability intersections because of these double counting problems. So you subtract P of A and B minus P of A and C minus P of B and C. But after that, if you kind of look attentively, kind of, and with this diagram or kind of on this kind of a proof, then you'll figure out that this time you subtracted too much, right? And it turns out that you'll need to add back some of the probability. So, and it turns out that in this case, you need to put probability of triple intersection. And so, and this is it. And this is naturally generalizes for kind of any number of elements. You write the formula the same way. And the only thing that is not clear immediately whether it kind of should be, maybe you should some point you'll need to subtract twice, kind of, or 3 times. But no, kind of, it's always the same formula. So you start with the sum, subtract the probability of double intersection, add back the probability of triple intersection, subtract the probability of quadruple intersections, and so on until kind of you get to the final intersection of all the sets, and you take the sign which is kind of plus or minus in this case. And so this is, well, this is a sometimes useful formula, but I've seen that it's used, but kind of not very frequent. This is kind of very useful formula, kind of the probability of the union of the two sets. So this is very useful, but in more restricted set of the circumstances. All right, so let us see. Questions? And so now, all right, so maybe kind of this is all for today. I'll have one poll asked to you, kind of, so maybe do not leave yet. So maybe kind of I ask